Okay, so today we're doing derivatives, day 3. The first day I taught you how Newton came up with a derivative idea, or others like him. Okay? The second day, we actually just did some examples together. So we did rad x, we found the derivative, and we did sine x. And I think the answer for sine x was kind of surprising. So let's review that yesterday, our takeaways from yesterday. We actually learned 3 facts yesterday. Can someone remind us what they were? Just 3 facts. Henry? Yeah, so from yesterday, you're right. We learned that if f is sine x, then the derivative, f prime, is, what'd you say? Cos x. That's right. There's so many ways to write this, folks. F prime equals sine x gives us f equals sine x yields f prime being cos x. You can write it this way. Watch. This is notation frenzy here. d dx of sine x equals cos x. That means the derivative of sine x is cos x. Okay? Some people write it like this. Sine x with a prime on it is cos x. And I regret to tell you, but there are many, many other notations. Even capital D sub x of sine x equals cos x is a popular notation, I think, in the Barron's textbook. It might be Barron's. There might be a different one. Kaplan. One of those review books, they use this symbol. But listen, I don't use that one because we learned Kramer's rule this year, and that means something totally different in matrix, remember? But it's a valid one, and it's accepted. So primes and ddx's and also this capital D thing. And there are others. So sorry about that. There's another 2 takeaways. Actually, they were responsible for helping us come up with this first takeaway. What was it? Do you remember? Jason? Not 0, but 1. Yeah, this is a surprising takeaway, and it's one that everybody memorizes. It's in the old calc standards for California. Okay? Standard 1.3. It's on the wall over there. It's the 4th one down, even though it's standard 1.3. But anyway, that's in there. And then there's one more takeaway from yesterday. Another special limit, in fact. You remember that one too? Okay, go ahead. That's right. Okay, everybody memorizes the 3 things that you just heard. Okay? In fact, you can't do the derivative of sine without these 2 facts, really. Not very easily. Okay? If you remember my proof yesterday, I used both of these to come up with the first takeaway Henry mentioned. And then over the weekend, you guys are going to be taking the derivative of cosine for me. All right? And you're going to need these special limits again. So I need you to know what I did yesterday. Did anybody miss yesterday? Okay, you need to watch the video. Okay? You have 2 options. One, you can research the problem cos x and figure out the derivative. You can use online sources, whatever. You got to show the proof for it. Okay, and then go back and try sine x on your own. Or watch my video on sine x and try cos x on your own. You need to try one of them without help. I'm telling you. The only help you should have is somebody's notes. But if you don't try one of them on your own, you'll never learn it. Okay, there's actually a 3rd special limit that's really important. And it's e to the h minus 1 all over h as a limit of 1. But I'm not teaching that one today because it has nothing to do with what I'm teaching, and you won't need it at all until mid-chapter 3 next year. So I'm going to put that one on the back burner, but just know there's one more of these guys that we'll get to later. So those are our takeaways from yesterday. And the title of my lesson today is The Shortcut, or how about this? Are you sick of f prime of x equals LIM, h goes to 0, f of x plus h minus f of x over h. This is the title of my lesson. Are you sick of it? Because if you are sick of it, today we're going to develop a way to get around this formula and not need it so much. Okay? Are you guys sick of this formula? You haven't used it too many times. You're going to use it this weekend. You're not allowed to use the shortcut I teach you today on this weekend's worksheet. Okay, you cannot use it. You have to use this horrible formula one more time. One more worksheet, please. But I'm teaching the lesson a day early, and then Monday night you'll get to use a shortcut. Okay? All right. So we're going to actually use this horrible formula to find the derivative of this expression. F of x equals x cubed plus 14x squared plus 6x minus 12. We're going to use this horrible formula one last time. When we see the answer, we're going to suddenly realize, wait a minute, we could have done this so much faster. We're going to write down our conjecture. We're going to go back and prove it. And then we will stop using this method. Okay? So let's try to find the derivative the long way. Or as my son says, the long cut. He's 4. I told him there's a shortcut on this one board game we were playing. And he's like, I like long cuts. I don't think he understands. Okay. Remember, this is a horrible thing. For now, it's limo, big fat fraction. H on the bottom, remember? Function with x plus h's in it. X plus h cubed plus 14 times x plus h squared plus 6 times x plus h minus 12, all minus, in parentheses, x cubed plus 14x squared plus 6x minus 12. And every year there's some student who doesn't put parentheses on. So what happens? They forget to distribute the negative, and then their terms don't cancel properly. And then they usually just get undefined in the end, or a missing term or something, or too many terms. Yeah, or they give up. They come to me and they say, what's wrong? And I quote my famous saying, Useth parentheses. Maybe remember that from my Algebra 2 days, when I taught you Algebra 2, your Algebra 2 days. Okay, so we've got to work this out. It's kind of a pain. This first term is kind of the most stressful term right here. But remember, we can use Pascal's triangle for such things. So don't forget to park the limo out front. We get 1x cubed plus 3x squared h plus 3xh squared plus 1h cubed. That is the expansion for x plus h cubed. It has coefficients 1, 3, 3, 1. Remember the Pascal triangle? Okay, next term. Not as stressful. It's just a FOIL and then a distribute of 14. But it's going to be x squared plus 2x h, plus h squared. Then you distribute into 14. So it should look like this. 14x squared, 28xh, 14h squared. That's our middle term, or our second term. And the rest isn't stressful at all. It's just distributes and stuff like that. Okay, so then we have a plus 6x, a plus 6h, a minus 12, a minus x cubed, a minus 14x squared, a minus 6x, a plus 12, excuse me. Glad we used parentheses here. Don't forget to distribute that minus. And there's two promises that I always make. One, anything that doesn't have an h should vanish by subtraction. So goodbye x cubed. Who else has no h? 14x squared. Yep. Goodbye. 6x. Gone. Negative 12. Gone. The only survivors are terms with h's. If you see any rogue terms chilling in there that have no H, you did something wrong. Probably you didn't distribute minus. Okay. Since everybody now has an H on top, we can pull out an H on top. So you've done this many times, but just one last time to get it right, you know. Pull out an H on top. I guess we don't need this much parentheses now. What survives here? Well, if you pull out an H, you get 3x squared plus 3xh plus h squared. A moment ago, this term had more h's, but we pulled out one of the h's from the green there. Plus, and then there's a couple yellow terms that survived. Oops, yellow. We're pulling one of their h's out, remember? So this is 28x plus 14h. And then the h cancels out by division. Good riddance. What about the 6? Ah, there is a 6h. Hello, lonely 6h. I forgot about you. Put me back in. Okay, come on in. We pulled your h out, though. Oh, man. It's out front. Oh, okay. Yeah, thank you. There is a 6h there. And all the h's shout, all the h's that survived shout, we made it. We didn't die. Well, you just wait. We still have one more thing to do, don't we? So our terms with h's shouldn't be too excited right now, right? What's going to happen to all the rest of the terms that have h in them? It's time to plug in 0 for h, right? Don't forget the last stage of the problem. The answer is 3x squared plus 28x plus 6. Okay, now, this is our answer. Can someone remind us what this thing's job in life is? He has one job in life. What's his job? Find the slopes. Whose slopes? Function, right? The original function was a graph. That graph has slopes. This guy will tell us all the slopes. Very nice. Welcome to the family. I feel like we just got a brand new superhero, you know, just born. That's his job. That's what I said yesterday. I already said that, didn't I? Let's look at f, and let's compare it to f prime, and see if we can come up with a much, much faster way of doing this problem. This problem was x cubed plus 14x squared, remember? Plus 6x plus, or minus 12, remember? This was the original problem. Let's not shout it out, but look at the terms here, guys. Maybe there's a faster way to get f prime next time, because that was a lot of work. That's a triangle, blah, blah, blah. I'm not going to take any hands yet. I want you to look at it. I want you to think about it. How did that x cubed turn into 3x squared? How did that 14x squared turn into a 28x? How did that 6x turn into a 6? Why is the negative 12 gone? Think about it. You have a question, or are you going to give an answer? I don't want answers. I want thinking. Jack Stein gets the answers in under 10 seconds. Everybody else, think about it. Or maybe you already have the answer. Maybe you were already taught this trick, but you didn't know why it worked. You still don't know why it works. We're going to prove it in a minute. Notice that the black terms, don't miss this. Some of you tune me out so often. I'm probably not exciting enough. Notice that the black terms are all one less power. See that? X cubed, x squared, x. 6x became 6, no x's. That's part of the trick. You take away one of the x's. You diminish the degree by 1. But the coefficients seem to change. The coefficients used to be 1 and 14 and 6, but now they're 3 and 28 and 6. Anyone know how we switched over? Okay, Jack, now I'm ready.
Okay, you put the x on top, like if you have x
You put the
Well,
3.
bring the 3 down, essentially. And then you subtract the top part by 1, so you get 3 times x squared. And then for 14x squared, to bring the 2 down, we'll do 2 times 14x. And then for...
Why x?
Because you subtract 2 minus 1.
So you lose a degree?
Yeah. And then for the 6x, you do the x.
Now what's the power on 6x? What's the
X
power
to
on the
the
x?
first.
It has an x to the first, right? So, give me in 2 short phrases the 2 things you do.
You subtract the power by 1, and you put, well, in this order, you would bring the exponent down and subtract the previous power by 1.
Okay? Bring the power down to the front. It becomes one of the factors of your coefficient. So it multiplies in. Then diminish by power. It's that simple. Bring the 2 down. This now is a 6. Take away a power. Now it's x. I'm sorry. Bring the 3 down. Now it's a 3. Take away power. Now it's x squared. Bring the 2 down. Now that's 28. Take away power. Now it's an x to the first. Bring the 1 down. This is still a 6. Take away power. Now it's x to the 0. Nobody ever writes x to the 0. But what happened to the negative 12? What was the derivative's job in life? What is his job in life, the derivative? Find the slopes. What is the slope of the line y equals negative 12? Y equals negative 12 is a horizontal line with slope 0 everywhere, and the derivative reports back to us that this term will not affect the slopes. After all it is a downshift. It won't affect any slopes. How can it affect the slopes of a curve by just dragging the graph straight down? It won't. So this guy has to do a shifting. He will not play a role in the sloping of the graph, f. So it vanishes. We never include the constant term when we take the derivative. The derivative is bring down the power, diminish by power. If you're dealing with a constant term, just get rid of it. Question?
Can you use that trick to find integrals?
Almost. Almost.
You wouldn't
It's a
go-
reverse thing.
Yeah, well, no, I figured.
Integral, by the way, is when you start with the black and you try to come up with what you think the blue was. Okay, so what we just did was we started with the blue and we created the black and we found the connection. But if you wanted to work backwards, you can almost do it. What you could say is, well, this is a 3x squared, let's see, so that 3 must have come from the old power. Or no, I'm sorry, I need to add 1 power, so that'll become an x cubed. And then, I need to divide by 3, because that 3 was originally not there, so I have to undo it. So you can kind of work backwards and figure out, well, that must have been x cubed, that must have been 14x squared, that must have been 6x. The only problem is you'll never know that this was a 12, because it could have been a 1,286 pi, and it would have vanished. All constants vanish, so you don't know what this number is if you're trying to work backwards. But the rest of it you can figure out. In other words, don't worry about working backwards right now. It doesn't even work perfectly. Okay? You'll end with an unknown constant. But for now, know that we have just developed a hypothesis, right? We've just come up with this idea. What is our hypothesis? Something like if a function is a number times x to some power, then we believe the derivative should be, how does the trick work again? How do we do the trick again? Bring the n where? To the front. Does that mean it replaces the a, or what do we do with it? It multiplies n with the a. So now the front is a n. And then what do we do with the old degree? Diminish it by 1, right? This is our hypothesis. How much do we trust it? You shouldn't trust it at all. You shouldn't trust it at all because you haven't proven it. And even if it works on every problem you try in your whole life, you shouldn't trust it. Because proof is what allows us to trust things. Okay? So we're going to prove it. It's not that hard to prove. We're going to keep this function generic. We're going to call it ax to the n. We're not plugging in any values of a or n. Let's bust out and try this now. What would be the derivative if we stuck a limo out front, you know. We did this the long way. We put ax to the n in here. This would be ax plus h to the n. If this comes out to what we predicted, na x to the n minus 1, then we'll believe it. We'll use it as often as we like. So some of you are cart before the horse on this. You memorize this trick to get through your calculus, your physics class. But now is the moment of truth where we finally see why it works. Okay? Also, actually, all of you kind of used it. Do you remember when I was giving you 2, 5, 10, 17? I was giving you sequences a while back. And you guys found the first differences. 3, 5, 7. And then you found the second differences. Remember that? And I said that if you have a constant second difference, that means your first differences are a linear pattern. Sure enough, 3, 5, 7, 9. And if your first differences are a linear pattern, then it's a quadratic original general term. Remember that? Well, there it is. You lost a degree when you took the derivative. And you lost the degree again when you took another derivative. This was very much related to what we're talking about today, but it was for whole numbers. So all of you have kind of used techniques in the past that involve slopes. But let's prove it once and for all. Here it is. We believe that this is going to come out to be an x to the n minus 1. Okay, so let's look at the left side, of course. Park your limo out front. Oh, goodness. How do we expand? Well, why don't we get the a out? Let's pull that a out. That a is just going to get in the way big time all throughout the problem. So we're going to pop the a out of the problem, put it all the way in front of the lim. You can do that. Ooh, it already kind of matches. There's an a in front on each side. Nice.
It's not squared.
It's not squared. You're right. It's nth power. We don't know what n is, and we have to keep it arbitrary. How in the world are we going to use Pascal's triangle if we don't know what n is? You know how to do it?
I think so.
Okay. What are we going to do with that?
Well, the first one's going to be x to the n.
Okay. So 1 x to the n.
And then the second one is going to be n minus
Okay, let's just work with the x's for now. The x's are going to diminish in power.
into x to the n minus 1 times.
Isn't there going to be an h term there?
Yeah, that's right.
Okay, yeah, I'm sorry. Go on.
And then it's going to be plus x to the n minus 2, h to the n minus,
Just h squared, right?
yeah, plus, that'll keep going forever depending on the.
What's the last term?
H
We're just, by the way, we're just expanding this part.
h
right
to
now.
the n.
You're right. This will all end with an h to the n with a 1 in front. And there's some Pascal numbers, you know. 1 and 1, you know. And then there's like an NC1 there, right? And an NC2 right there. Blah, blah, blah. You're right. Good. We still need the limit. Mr. Shore has to write that in there, doesn't he? Okay, so that's all yellow. We will be canceling quite a bit of stuff in a minute. So there's still a limo out front. Always makes me nervous when there's a limo out front. Okay. Oh, minus x to the n, right? Look. Well, I made you 2 promises about something like this. Any term on top that doesn't have an h should, what? Cancel how? Subtraction. It works. My other promise was, since everything has an h on top, you can factor it out. Right? Okay, so we're not done yet, but we're getting there. Is this really equal to an x to the n minus 1? We hope so. Here's our left side as we stand right now. We're going to pop an h out. Now we have nc1 x to the n minus 1 plus nc2 I wrote that wrong. NC2, x to the n minus 2. There used to be an h squared here, but it's just an h now, because I pulled an h out. Plus dot dot dot. And what was our last term? 1h to the n. Well, we lost an h. We pulled it out, remember? So now it's 1h to the 1 less power, right? Is this really equal to an x to the n minus 1? We hope so. Okay, the second promise has been fulfilled. What did I promise would happen to the h on the bottom? Canceled. All the other h's screamed for victory. We survived, but not for long. What are we going to do next? We're going to make all the rest of our h's 0. That's what the limit process does. How come we didn't do that earlier?
Because we would have done it on the bottom.
We would have had 0 on the bottom. We can't have that. But we can do it now. All the other h's become 0, which really only leaves us with one lonely term. He's happy to survive. And boy, we're close. I hope NC1 is n. How many ways are there to choose one object from a group of n objects? How many ways are there to choose one apple from 12? 12. How many ways are there to choose 15? One student out of 15 students? 15. How many ways are there to choose one item from n items? N items. NC1 is n. We'll skip the factorial proof for that. We did it. Q, E, D, or I, D, D, I. I done did it. We done did it. W, D, D, I. Okay? You should feel good about that, especially since we get to use it, and it is now a shortcut, a huge shortcut for us. So now let's practice it, because sometimes you might think, I can't use a shortcut on this problem, but you can. And sometimes you'll think, oh, I can use a shortcut here, but you can't. Okay? So we have to be very careful with shortcuts. Here's a problem where you can use a shortcut, actually. The problem we did yesterday. Remember the first problem I did yesterday? F of x equals x squared. I'm sorry, square root of x. I think I did. Square root of x was my example yesterday, right? Can I bring the power down and take away a power? I can if I write it as a power. Okay? So yes, if you write this as x to the half, you can do that yesterday's example, which took me 10 minutes, in 4 seconds. So make sure you title it f prime. This is your slope function now. Here we go. Let's all bring down the half. Put it in front. What else are we supposed to do? Not only do you bring the power down, but you also subtract 1 from the power, right? Well, what's a half minus 1? Negative half? Let's put this in radical form. The negative means on the bottom, the half means square root. Hey, that's the same answer we had yesterday. Except yesterday it took me 10 minutes. Pretty nice, huh? You like your new shortcut? You should. How about this problem? F of x equals cube root of x plus 1 over x squared minus 6x plus 5 all over x. Oh, I can't use a shortcut. This is like a new style problem. Oh, man. That's a good thought. You shouldn't be too hasty to use a shortcut. But I think we can make this problem work. Should I just like do the trick across the top and then do the trick on the bottom and then sort of just reduce everything? No, I didn't tell you that you could find the derivative of a ratio of two functions using trick on top, trick on bottom. We never said that. We need this to look exactly like the style of problem that we used earlier, where it's something plus something plus something plus something, you know? So you need to sort of break this up into multiple terms. It's very important how it's written. If it isn't written the right way, you shouldn't be using the shortcut. okay? All right, so let's rewrite the problem. We're not doing any calculus, we're just getting ready to. Split it up into 4 terms. Maybe write this as, x to the 1/3 over x to the first, x to the minus 2 over x to the first. This is just 6. Maybe write this last term as 5x to the minus 1. I think we're almost ready for the shortcut. I don't feel ready quite yet. What's x to the 1/3 divided by x to the first? You're subtracting, right? So 1/3 take away 1. So we're not doing any calculus. We're getting ready to. This is x to the minus 2/3 right here. What's negative 2 take away 1? Negative 3, right? The last 2 terms are already kind of prepared and we're ready for the shortcut on those. Okay, now that we have the whole problem looking like a polynomial, I think we're finally ready for the calculus. Now listen, a lot of students every year, a couple students every year, get to here and they feel so good about it, they stop and circle it. Did they find the derivative? No, they rewrote my function 4 times. Right? This guy's job is still to find the y-coordinates. That's not the slope calculator, is it? Okay, we need to get the slope calculation function. So now we get ready to do our trick. Okay, so how does the trick work again? We call it f prime, or ddx of f, or whatever. We bring the power to the front, take away a power from the power. So be careful with this. You're supposed to diminish negative 2/3 by a whole. So you're going to be taking away 1, see? From negative 2/3. Be careful. What does that give us? Negative 5/3. Yes. The next term is actually going to be negative. Because what do we do with the power? We bring it down. So this is actually a minus 3x to the minus 4. See? What happens to the negative 6? Why?
Because it doesn't affect the slope.
Yeah, it's a shifter, and it's not going to affect the slopes of a curve. If you slide a curve straight down, all the slopes stayed intact. Or you could think of it this way. Y equals negative 6 is its own little line, totally horizontal, and has no slope, has 0 slope. Okay? So anyway, constants just disappear. If you want to put in a plus 0 here, you can, or just leave it out. The next term is negative. Why? You bring down the power, right? So when it comes down, it makes that a negative 5. And then we diminish the power by 1. Be careful here. If you take away 1 from this old power, you get what? Negative 2, not 0. Right. Now, since the problem was originally written using, like, radicals, I think you should put it back into radical form. That's how I feel about it. But there's nothing wrong with this answer. And if you want to find a slope at x equals 4, or whatever, plug in 4. Okay. Your worksheet tonight, you're not allowed to use this trick, okay, unless the problem says you may use the shortcut. But this officially is called the power rule. The power rule for derivatives. Have a fantastic weekend.